Welcome back, everybody. This is 2015 Calculus AB number 5. It's going to be a graphical analysis. And note, we have the derivative of f. F is twice differentiable, so f prime and f double prime both exist. We have horizontal tangents at these 3 points. What does that mean? It means that at those 3 points, at -1, 1, and 3, if you were to draw a tangent line, they would be horizontal or have a slope of 0. Bam. Part A asks us, find the x-coordinates, not the x and y, just the x-coordinate, where the function f has a relative maximum. The first thought that should come to your brain is the derivative must change from positive to negative. Well, this is the graph of the derivative here. So where is the derivative negative? Everywhere at this pink shading. Where is the derivative positive? It's going to be above the x-axis. I will do the purple. That's where it's positive. So clearly it changed from positive negative at -2. Right at this point, it goes from purple to pink, or positive to negative. So that's our answer. So we just need to state that. For part A, f has a relative maximum at x equals -2, and you need a reason because what's all that stuff showing up there? That's weird. Because f prime changes from positive to negative. Done. Let's do part B. All right, so this one's going to be more work. We want f to be concave down and decreasing. When are both of those happening? So I'm going to get rid of this purple. F is decreasing when f prime is negative, and f prime is negative here. So let me go ahead and kind of give you the game plan of what we're going to write. So here, f prime is negative, implying that f is decreasing. So that's how we're going to get the decreasing portions. Concave down. So looking at concave down, that occurs when the second derivative is negative. So how are we going to get the second derivative negative? Well, let's look. We have the first derivative. What's the relationship between the first derivative and the second derivative? Well, the relationship between any function and its derivative, if that function is decreasing, its derivative is negative. If that function is positive, its derivative is positive. So for the second derivative to be negative, f prime would have to be decreasing. So I'm going to do that in this. Whoa, I didn't mean to do that. In this. So on that beautiful pinkish, violetish highlighting, that is the sections where, I guess I'll use that. The sections where we have concave down. So here's the logic. In those pink sections, f prime is decreasing, implying that f double prime is negative, implying that f is concave down. So that's what we have to write, the actual justification, the explanation. So we're going to do that. I wish I left myself more room, but I got an idea. I'm going to do the purple part first. So f prime is decreasing. Then I can erase the other purple part. F prime is decreasing on what intervals? So we're looking from -3 to -1. And where else? Looks like 1 to 3. Therefore, f double prime is negative on those intervals. Why don't I stay with one type of writing? You know what? I'm going to bother somebody even more. All these things are popping up out of nowhere. They won't go away. On those, okay, intervals, therefore, f is concave down on those intervals. Bam. So that's going to allow me to erase all this. So we have just defined the regions where f is concave down. Now we're going to do the part I wrote in red. This stuff, I'm just going to write it in words. So f prime is negative. You know what? Much easier just to say this. On what intervals? Now I'm going to break it from -2 to -1, the open interval between -2 and +1, and 1 to 4, period. Therefore, f is decreasing. Yikesies. Whoa! Did you see that? That's weird. F is decreasing on those intervals. All right, that's pretty much it for that part. Now, the reason I didn't do from -2 all the way to 4, at 1, f prime is 0, not negative. So that's why I didn't include that. I think if you included it, they might let you slide. I don't know. Now we have to have our final. We got to find where it's both, the function's both concave down and decreasing. Basically where the purple and the pink are together. So here to here and here to here. So therefore, f is concave down, and sorry, I keep switching between script and print, and decreasing on the interval from -2 to -1 and 1 to 3. Whoa, that is, yeah, magic. That's ghosts, something's so going on, that's weird. So that's the answer for part B. That's only B. My brain's tired already, and we've only gotten to B. That's sad. Part C, points of inflection. Okay, this is good news. We're going to save our work from part B. Some of our work from B we're going to save. So that these regions I have here, we already determined that's where f is concave down. So let's pick another color. Let's do this color. Here and here, that's the region I'm going to focus on. So what we're going to say on those regions, here's our logic we're going to go through. F prime is increasing, implying that F double prime is positive, implying F is concave up. So we're going to make that argument in part C. So part C, F prime is increasing on the intervals from -1 to 1 and 3 to 4. That, yeah, spooky things. And 3 to 4, period. Therefore, because of that, f double prime is positive on those intervals. Therefore, f is concave up on those intervals. So we have defined the regions where f is concave down. We've defined where f is concave up. And where do they switch signs? I will do it in what color? Blue. So here, here, and here. Those are going to be the inflection points. So therefore, a lot of therefores, f has inflection points. Whoa, that was bad. Inflection points at x equal -1, 1, and 3, because it's not because concavity changes, it's because f double prime changes signs. That is frustrating. The pen just does weird things. Changes signs. I didn't do that. It's a ghost. Changes signs at those points. That is so freaky. I don't know what's going on. See those dots appearing out of nowhere? I don't understand. It's frustrating. Oh well. You OCDs, you got to deal with those dots. Sorry. All right, part D should go pretty quickly. Part D, so you're given f at 1, and you want f at 4. Wow, that is weird. It keeps doing that. That's not me. Not me. Oh. Those were me. Those dots came randomly. Okay, so part D. This is fundamental theorem. You want the value of the function at 4. You know where it starts at 1. So if you can figure out how much the function changes from 1 to 4, and you add that, but we do know that, the fundamental theorem of calculus. We have to simplify that. F of 1 is easy. It's given as 3 right here. Now, other information, we were told the area of this region is 9 and the area of this region is 12. We were told that. So we want the integral from 1 to 4. So if we integrate from 1 to 4 going to the right, it's the net area. And the net area is going to be -12 because that's underneath the x-axis. So that's going to be plus -12. That's your answer. Stop. Don't do anything else. You'd be foolish to go any further. All right, then they want f at -2. Well, it's the same concept. I know the value at 1. If I know how much it changes as I start at 1 and go to -2, that is so bizarre. I'm not making these marks. Believe me, I'm not going crazy. I know you might think I'm going crazy because we're stuck at our houses and those things are appearing out of nowhere. And that 4, I didn't write a 4, did I? I put X, right? I'm not. Yeah, it's a ghost. All right, so f prime of x dx, which is easy. F of 1's given at the beginning of 3, but then we're integrating from 1 to -2. We're going this way. Now, you do the net area still, but you do the opposite because you're going backwards. The net area is -9, but since we're going right to left, it's going to be +9. Stop there. Don't simplify any further. That's it. This iPad's possessed. It just does whatever it wants. It's not me. It's not me.